Hi. Hello, everyone. First of all, I want to thank you for inviting me, especially thank you to Chris Hayward for hosting me. It's been a pleasure. Just so you guys know, I am actually a visiting scholar here, so I usually sit on the sixth floor on Thursdays, every Thursday. So if you want to talk later about my research or about your research, I'd be happy to meet with you. So today I'm very excited to talk to you about intensity mapping, and particularly in the context of constraining the interstellar medium. So this is important because with intensity mapping, we have a grand opportunity to be able to map very large cosmic volumes, which you normally can't do with traditional galaxy surveys. And so this will allow us to learn more about the total population of stellar resolution in various galaxies and how stellar and galaxy evolution evolved. And it can also give us some hints as to whether we can use this method in order to actually probe large-scale structure and cosmology. So this is work that I've done over the past few years with several collaborators. Three very important collaborators I want to just highlight are Shang-Chi Yang, my graduate student, as well as Eric Switzer and Chris Anderson from Goddard Space Flight Center, and Rachel Somerville at CCA. So first of all, just as for those of you, just as a review, I want to just present the basic idea behind cosmic dawn. So cosmic dawn is the point in time in which which we believe that stars first ignited in the universe. So before then, we had a period called the Dark Ages, where this was basically from the redshift of 1100, when recombination occurred, when the first atoms were formed, into all the way to the first stars, when you basically just had neutral hydrogen and helium and some trace elements. But cosmic dawn which took place 400 million years after the Big Bang, was when the first stars began to ignite. These stars weren't exactly like our own. They usually have massive. These are known as Pop-3 stars. But as they began to form with, and also matter began to cluster in galaxies, you began to have more stellar evolution. And particularly in this time, the universe transpired from a neutral state, where hydrogen was neutral, into an ionized state, where hydrogen exists in an ionized form. And so in this case now, as this began to take place, you also had the stars also began to change, because as you had stellar evolution and stellar nucleosynthesis, you began to have more heavier atoms and molecules. And so this seeded in order the structure of the universe and the makeup and the chemistry of the universe as we know it today. However, there's still lots that we don't understand about stellar evolution and galaxy evolution. In particular, we know that as you map the stellar evolution, in particular, what we call here the star formation rate density, or the mass of stars produced per volume. We have a plot here, the famous Madal plot, where you have we see that at redshift 2, so about 10 billion years ago, the number of basically the density of stars began to decrease, and it has decreased today by a factor of 20. Whereas we know that the dark matter structure, a lot of the large-scale structure that you normally study when you're looking at galaxy surveys, that has increased by a factor of 100. And so what is the nature of this discrepancy? Well, there are various models, but we're not sure what is causing this discrepancy. Also, too, we know that only 5% of baryons actually has been converted into stellar matter. And so in particular, these facts aren't fully explained. However, if we were able to map the gas emission in the universe, this would allow us to probe the interstellar medium, or ISM, and stellar evolution in order to begin to answer these questions. So there are multiple lines that you could particularly use, and there's been many galaxy surveys looking not just in the optical, but also in the infrared and various regimes and radio, in order to be able to answer some of these questions. So in particular, one line that we all know is the 21 centimeter line, and this traces both neutral hydrogen in the IGM, or intergalactic medium, during reionization, as well as neutral hydrogen within galaxies post-reionization. We also have other molecules in other lines that are also very useful in tracing star-forming galaxies. For one, there's this CO line, or carbon monoxide. This traces coal gas, specifically, and in particular, neutral molecular hydrogen within galaxies. You also have the C2 line, which traces star formation both within clouds, inside for clouds inside the ISM as well as between clouds. And then also within the ISM. And also you have alignment alpha, which traces star formation both in the reionization and post-reionization regime specifically. And a lot of people are also looking eventually for cross-correlations between alignment alpha and neutron hydrogen. And just to get a picture of where these lines show up in the spectra, in case you weren't aware, you can get a spectra that looks like this, where you have molecular, where you have CO lines, C2 lines. H1 is in the radio, so it's at lower frequencies, whereas alignment alpha is rest frame is in the UV, the higher frequencies, and of course these redshift over time. However, so we have particular galaxy surveys. Let's look at this. Some of the most common are ones like the VLA as a radio survey, as well as surveys in the microwave like ALMA. However, these surveys only look for the bright galaxies. Just like all traditional galaxy surveys, you're only going to reach the brightest galaxies. However, and so to get an example of how this can be a problem, if you look at this figure right here on your right, you can see that the red dots are, if you can have a map of what can be picked up by VLA. So the VLA can pick up, a very large array can pick up the red dots as the brightest galaxies in your survey, whereas all these gray dots are representing fainter, less massive galaxies that actually are more common in the full population of galaxies. And so we're missing a lot of structure from not being able to reach these galaxies. And this occurs not only just because you have this population, this numerous population of faint galaxies, but you also have galaxies that are at higher distances, and as a galaxy is farther away, it's fainter, and so you're missing, and so you're actually limited in how far we can look out in order to get a full statistical survey of cosmic volume by doing traditional galaxy surveys. So what can we do about this? Well, a method that has been in vogue now and is called line intensity mapping. So line intensity mapping is the idea that what you do is you measure the aggregate emission within relatively large angular pixels, like around pixels on the size of order of arcminutes or so. But the idea is that in each pixel you have hundreds of galaxies, and then in those pixels you can see all the emission, and you can look all the way out to cosmic time, and that allows you, in order to be able to map the sky fast and to be able to see out much farther back in cosmic time. And so this will allow you, and you can look at this in two ways. So particularly when we want to do this, we want to look in both angular space and frequency space, particularly because angular space allows you to see transverse directions on the sky, whereas frequency space will allow you to look back in time as lines redshift over time. And so as we look at these 3D volumes, you can begin to sample the clustering regime in very large cosmic volumes. And so this will allow you to see much larger volumes and much farther distances than you can see with the traditional galaxy survey, because you can now pick all the emission, because the massive halos that you can measure with intensity mapping are much smaller than what you can see with the traditional galaxy survey, on order of four orders of magnitude. So you can also do statistics with this, just like with these fields, just like you can do with a galaxy survey. So you can also measure power spectra. So you take your intensity map in 3 dimensions. You take the fast Fourier transform it, and you can measure auto power spectra, sort of like this fiducial this forecasted picture here that will be measured by the time C2 mapper during reionization. And so the idea is that you can see various regimes. So you can if you measure power spectra at both large scales and small scales, you can also pick up the shot noise, which is another tracer of the intensity of these lines. In particular, what you would measure is that by measuring the power spectra, you measure in terms of the luminosity function, or like the histogram of luminosities that you would measure. The power spectrum, because the power spectrum would be a way to measure the first moment of the luminosity function, whereas the shot noise would measure like the second moment of the luminosity function. And so and then you also will trace, and this would also be proportional to the power spectrum, just like in galaxy surveys, and so you would indeed be able to potentially trace large-scale structure.
Can I ask a question?
Yeah.
So the first and second moment of the luminosity function, is this a precise statement or just a rough statement? I mean, to me, that's the mean and variance of the luminosity function.
Right. So it's a precise statement in the sense that the intensity of the average intensity of a line can be modeled as modeled in terms of the luminosity function. The idea being that luminosity function relates to the halo mass function, which produces with which stellar evolution happens and produces the lines. And so, and in particular, if the shot noise is Poissonian, which is an assumption, but if the shot noise is Poissonian, then you can then that naturally will model the second movement.
So if I take my luminosity function, I remove the exponential cutoff and put a long tail, so there are a few really bright objects out there, it doesn't affect any observables, right? It doesn't affect the shot noise.
Well, no, that's what I'm saying. Like that will all be included in the luminosity function, and that would affect the shot noise.
Okay, because I'm changing the variance.
Yeah,
Okay.
That's right. Okay, but as we know, as all of you experience CCA, for any of you who are in CCA, you know that not all the information is contained in the power spectrum. There is so much more statistics there, much more statistics than I would care to, be able to care to understand. But you know that there's more information out there, and we can always squeeze out more information. And one candidate, in order to squeezing out more information from intensity maps, is called the voxel intensity distribution. And so this is a lot of work that was pioneered by Patrick Brees at CETA. And the idea is that you can actually measure, just take the intensity maps and basically measure the histogram of intensities within each pixel, and this actually contains information. In particular, it's basically a direct tracer of the luminosity function itself. And so this is this could be a very powerful tool, and and also Patrick has been working on updating this statistic over time, in particular developing ways in order to remove the foreground signal from this. And one idea that's very tantalizing is the idea that if you can use the voxel intensity distribution, or VID, and the power spectrum together, you can use both of those pieces of information in order to separate out effects from astrophysics and effects from large-scale structure of the power spectrum. And so you can use this in order to allow intensity mapping to trace both astrophysics and cosmology. So why intensity mapping? Well, there's some hints, but there's several things that we want to be able to show with intensity mapping, including star formation, as modeled here, where these crosses are what we can do normally today with UV surveys, but with intensity mapping, like with CO, we should be able to do a lot better. Also, we want to trace ionization. Again, because you're able to see structure out into farther distances, you can begin to have statistical analyses of traces in very high distances, which you normally can't do as well with traditional galaxy surveys. We also want to look at, again, the different lines in the interstellar medium, because they trace different constituencies of the galaxies, different gas populations, both hot, ionized, and cold. And in addition, we want to be able to use the intensity map for large-scale structure and cosmology in particular. So with being able to survey large areas in the transverse direction really fast, intensity mapping, as it develops more and as it is able to reduce foregrounds, it could be able to potentially compete with upcoming galaxy surveys like LSST and Euclid. And then because it can see much farther distances than normal galaxy surveys, then it will basically be really the best game in town in order to trace very high structure at very high redshifts. So one major challenge for line intensity mapping is, of course, the foreground. So unlike the CMB, where the foregrounds were at the right frequencies around 70 gigahertz, the CMB actually is greater than foregrounds from the Milky Way galaxy. That's just not the case for intensity mapping. The fluctuations are much smaller, orders of magnitude smaller than for the CMB. And so in particular, in many cases, the foregrounds can range from 100 to 10,000 times greater than the signal. And of course, if you're measuring a power spectrum, that squares that, so it's even worse. In particular, although one silver lining to this is, at least for single dish surveys, where you use a single dish in order to detect the intensity, you actually have the case where when you take the Fourier transform of the intensity map, any foregrounds can come into continuum emission, and so those continuum emissions tend to contaminate large scales along the modes of large scales along the line of sight. And so basically, this is sort of a map of what a foreground will look like in Fourier space, where your continuum foregrounds will basically populate this lower region where you have large scales along the line of sight. And so if you're able to part with those modes, then that could help eventually in 21 centimeter surveys in order to be able to detect the power, in order to detect fluctuations in intensity that you can relate to the large scale structure. Now, of course, this hasn't been detected yet. We are able to detect cross correlations, but we haven't been able to detect the autocorrelation yet. But as we get better with foregrounds and increase in sensitivity, this should get better and better. In particular, though, cross correlations help with this because, as again, we haven't detected the auto, but the cross correlations have been done by various. We've seen the cross correlations for about 10 years, over 10 years now, and in particular because with cross correlations, if you cross correlate, for example, an intensity map like 21 centimeter with a galaxy survey, those two traces don't have the same foregrounds. And so even though there's this foreground from the Milky Way in your 21 centimeter map, that shouldn't correlate with the at least to a large extent with any foregrounds in the galaxies. And so when you do a cross correlation, basically those fluctuations from that foreground fall away, and so you're left with the signal. Now, of course, they still could contaminate the errors, and of course, you have to be really careful. There are certain sets of foregrounds that you still want to that, for example, bright galaxies could emit in both frequencies, in both radio and the optical. So you still have to worry about those things. And of course, even in addition, if you have, particularly this is a problem for if you want to cross correlate two intensity maps. If you have, if you have line emission, that could also, particularly even without that, with line emission, you could also have contaminants where you aren't isolated in this large scale regime, and then you have to worry about those. And so that's what lots of people in these instrumental surveys are working on. So I was interested in this in particular. What I wanted to do was see if you could map lines with large scale structure, with intensity maps. However, in particular, I wanted to do an actual data analysis where using what we have. And so specifically, I wanted to use the Planck maps in order to be able to constrain C2, which should emit in high frequency Planck maps, in what we normally use in order to capture the dust. So again, we normally use it to capture the dust. So so the problem is that if we wanted to use those Planck maps, here's a map of the Planck 545 gigahertz map where I masked out the middle of the galaxy so you could see fluctuations. And so the thing is that with this, you still have some trace galaxy, you still have some Milky Way galaxy emission, which you can see in these red parts. But also at the poles here, where at these poles here, you also, even though you don't have very little galaxy emission, you have other emissions for continuum emission from extragalactic sources. In particular, this source of emission is called the cosmic infrared background, which comes from dusty young stars in our cosmic volume. And so in particular, you can sort of see, like, in particular, the line I was looking for is the C2 line, which traces star formation in the ISM. And in particular, if you want to think, well, how big are the foregrounds compared with this C2 emission that I'm trying to detect? Well, the dust is about 12 times higher than the C2 for the Milky Way, and the CIB is about 7 times higher in intensity. And so this is something that we want to say, well, if these foregrounds are dominating our signal, how can we detect it? Well, of course, as I talked about, cross correlations are a good way to go. Particularly, what we tried to do is we wanted to say, well, if we could cross correlate C2 at high redshifts with quasars from Sloan Digital Sky Survey, specifically SDSS3 or the BOSS extragalactic survey. What we can do is, since the idea is that, well, the dust from the Milky Way shouldn't cross correlate with these quasars because those are at different redshifts, they're different parts of structure, they should not be correlated. In that case, then if we do a cross correlation, those should fall away. However, this is not true for the CIB. CIB is extragalactic, so it should indeed cross-correlate with the quasars. So we couldn't expect that it would all fall away. However, luckily for us, Planck doesn't have just one band; it has multiple bands. Obviously, it wouldn't be able to do science otherwise. But that helps us because what we can do is we can expect that although C2 should exist in principle in all bands of Planck, they would exist at different redshifts, and in particular, those redshifts wouldn't. In the C2, if we cross-correlate basically all these maps with the same finite redshift range of quasars, the C2 at different redshifts should not correlate with these quasars. And so what we can do is we can expect that for these three bands, the 340, the 353, and 545 and 857 band, if we cross-correlate all of those with only quasars from redshift 2.5, or around that range, then any C2 at these redshifts for the other bands would not cross-correlate with our quasars, and those would fall away. And so we can use this in order to build a model where, in our model for the power spectrum, we expect to have CIB for all the bands cross-correlated, but we only expect the C2 at the redshift we're looking at to only exist in the 545 band. And so we can use this, and we can make a joint model of CIB and C2 emission, and use use the information from all that to constrain it. And in addition, just to add on some extra power, we also used cross correlations with galaxies at redshift of 0.5 as well. And so this is work that I did in 2018. Actually, with Shirley Ho at CCA was one of my collaborators for this. And what we found was that although we were able to make a measurement, it was not a detection. So this is sort of an amplitude that we measured for representing what the intensity would be. And so it was definitely less than 3. It was just a little over 2 sigma. And so we did not have a detection. In a later paper, and this is work that I started collaborating with Eric Switzer, and also my student Sheng-Shi Yang was a collaborator on this. One thing we considered was, well, could we improve this? Because when we did this previous analysis, we didn't consider if we could remove Milky Way galaxy from the air. So any foregrounds existed in the airs, even though they fell away from the signal. So we wanted to say, well, could we actually do a better job to remove the errors? And specifically what we did was we used templates of the Milky Way galaxy. One, in particular, one was H1 map that was constructed by Daniel Lenz. And so what we tried to do is we tried to use those as templates in order to try to remove the Milky Way galaxy using those templates. And so what we found, however, was that because we were basically trying to project out both the Milky Way and the CIB, we know that those spectra are very similar. They're both basically modified blackbody spectra. And so the problem is that basically you don't get any. Unfortunately, they tend to have basically the same. Well, not the same, but they tend to each have its separate effective temperatures, such that they're basically on top of each other. The contributions from the CIB and the C2 on this plot here. The x-axis is frequency, and basically it's basically while the blue band is sort of where our full power spectra are. You see the black and the red curve. The green and the red curves, the solid red curves, are both the contributions from the CIB and the dust. And so they are basically pretty much on top of each other, and so you don't actually get much power by trying to use templates. We did do some forecasts, and so we expect that once we have the full 3D information, once we're not using the broadband frequencies of Planck, but very high spectral resolution frequencies of intensity maps, we do expect to have much more information to be able to do a better job of separating those out. However, while we were doing this project, my graduate student actually had a great idea in order to increase the precision of the covariance model, the power covariance model that we were using to make our constraints. And so she was able to lead this project where Sheng-Shi Yang, where she was able to basically redo our analysis and show that you could actually get a higher signal-to-noise detection for the C2 amplitude. And so we were able to, by using what she developed, we were able to get a greater than 3 sigma detection of an excess, which we made some some constraints for the intensity and for properties of the ISM, specifically electron density and electron temperature, if you assume that that full excess was C2 emission. In the paper, we didn't actually claim that it was a full C2 detection because it's possible that if our CIB model had some errors in the redshift evolution of it, that you could possibly mimic what we found, particularly since we had broad bands for the Planck. However, we do expect, with this, however, if it was C2, this would be the intensity that we were able to detect. However, we do expect that, when we have full bona fide intensity mapping surveys, we should be able to definitively say whether we have a detection. Okay, so that's what we were able to do with broadbands, but we really want to be able to use intensity maps that are being developed now. So there are many intensity maps. This is a sort of an effort that seems like it's proliferated overnight, although I'm sure Dick Bond would care to disagree. There's a lot of work that went into this. In particular, in 21 centimeter, there's several 21 centimeters surveys that have a rich history, and now upcoming ones like HERA. It's going to map high redshifts, as well as CHIME is going to map CHIME and SPHEREx, which are mapping low redshifts, 21 centimeter. But now we have many surveys that are sort of in the pipeline right now for mapping lines different than 21 centimeter, like CO, C2, and Lyman alpha. Earlier today at the cosmology meeting, CCAT prime was mentioned, and so that's going to map basically redshifts, C2 and redshifts higher than 3. You have CoMap, which is going to map C2 and redshift around redshift 3. What I wanted to talk about are two surveys that I'm involved with. One is EXCLAIM, which is going to map CO and C2 at lower redshifts, CO at low redshifts, and C2 at redshift 2 at redshift 3. And then SPHEREx, which is going to, which one of its sort of sub campaigns is to do an intensity mapping survey of Lyman alpha and H alpha. So first I'm going to talk about EXCLAIM. So this EXCLAIM stands for the Experiment for Cryogenic Large Aperture Intensity Mapping. This is a project that I'm glad to be part of as the science lead, with Eric Switzer from Goddard as the PI. And so we're going to basically be able to answer some questions. We want to discover what factors led to the dramatic decline in star formation in redshift 2. We want to know about the abundances of molecular gas that form stars. We want to know how tight the relation between CO and H2 density is in galaxies, and we also want to know, be able to constrain some of these CO and C2 models to see how viable they could be at higher redshifts, or just at lower redshifts in order to do cosmology. And so this is going to be a survey that's going to be mounted on a balloon with an aperture of about 74 centimeters. And so what it's going to do is it's going to basically within one day, one night, a 10-hour flight, it's going to be able to answer our science questions. Well, it's going to do it over 2 flights, and as long as if we're lucky, which sometimes it's hard to do with balloon surveys, but if you are lucky, we could possibly fly it more and more and do more and more science. See, I'm not doing on time.
That's correct. 25 minutes.
Okay. Oh, I'm doing great. I finished early. Oh, we'll see. All right. So
what
yes.
are you flying?
So our first science flight will be in 2021. Actually, I have this information on the next slide, but 2021, and then that's first test engineering flight, and then the first science flight is 2022. We plan for 2 science flights. That's what's in the budget.
Where is it going to fly from?
Fort Sumner in New Mexico.
It's at Fort Sumner, so you don't have to worry about the vagaries.
Yeah. It's like, and right next door is Palestine, Texas, but that's more hard to get. So, yeah. Palestine, Texas, not the other Palestine. Okay.
But this would have great advantages.
Yeah, so and particularly it's going to be in the southern hemisphere, and yeah, it's more stable for the winter. Yeah, so it's going to map CO and C2. So in particular, okay, so I just want to talk about, so the frequency range is for 400 to 500 gigahertz, which happens to also be about 500, 600 microns. And so this is going to measure C2 at redshifts 2.5 to 3.5. It's going to measure CO, well, it's going to vary various rotational lines for CO at different redshifts, but basically in common, they're all going to be redshifts less than 1. For different redshifts, they're actually going to be, we're going to just split the frequencies up in order to cross-correlate them with different surveys. So these were modeled for just Bose galaxy surveys, but of course, we're going to have the information there. Obviously, STSS4 will be done by then, and so we'll have, and then it really is going to be even in the pipeline, possibly for cross correlations with DESI and other surveys as they come online, and information will be there. In particular, though, right now, well, I'll talk about the area later. It's also going to have a galaxy survey as well. One thing to note is here on the right are some forecasts for the intensities that we expect to find. So, so the top is the top cross is a previous constraint for C2 based on our work. And the bottom column says is a forecast for what we can do with EXCLAIM. In particular, the idea is that this would be able to more definitively answer what types of models best fit or better describe what the intensity of C2 is. In particular, we learn more about the various constituencies of C2 emission, and so that would be very helpful. In addition, at the bottom right are constraints for expected constraint for CO. Here, the x-axis is B times I, so this is the bias times intensity for CO. The different rows are different cross correlations between different CO lines and their corresponding galaxies of different redshifts. And then the dots are different models basically, and so the black bars are the areas that we expect for B times I. And so the idea is that we'd be able to also to constrain between those two. Now, this is just it's a very simple analytic forecast. I'm going to talk about later what we can do with simulations to sort of make this make this on a better footing. So here's what our survey would look like. So right now, as of now, the plan is to.
I just missed what the beam size is.
So the beam size is about 5 arc minutes.
5 minutes.
Yeah. So actually, I might have a good no. Okay. Yeah. So anyways, the plan is to survey stripe 82. So stripe 82 has been used in many surveys. BOSS has been used for many cross correlations with their various surveys, and so it'd be it's very advantageous for our purposes. In particular, CoMap is going to also map this region as well as HEADEX, which is alignment alpha emitter survey, and of course there are going to be many opportunities in the future. And so we felt that that was advantageous for us since we're going to do this in map the southern region. It'll be useful for us. Yes. Sorry. Okay. So and then there's the list of flights that we're going to do. Yeah. So this is what the telescope looks like. I'm not a telescope person, but this is what it looks like. Again, it's a 74 centimeter aperture. It's cryogenically cool at the bottom, so that's where it's going to be cooled to about 1.5 Kelvin. And this is going to be, it doesn't say on here, but this is going to be flying at about 100,000 feet. The idea being that it would reduce your thermal broadening of the line, so you can see between atmospheric lines in order to reduce your foregrounds in the atmosphere. Okay, so that's EXCLAIM. Now I want to talk about what I'm working on with my student. For EXCLAIM, particularly, what we're concerned with is, okay, let's say, let's say 4 years from now we have data, we're excited. Let's say we cleaned it. Assume it's all cleaned up. We did all our homework and we have clean data. And now we want to say, okay, well, what will we actually learn? Well, you can most of the models that we consider, particularly intensity mapping, we make analytic models. So we try to we try to say, well, we think the gas temperature is sort of like this, and we think the density of emitters is sort of like this. And so we put all these little ingredients together, we stir it up in a pot, and we come out with some analytic model for what their intensity should be. But the thing is that life doesn't always work out like that. Never does really. And so in reality. These, in particular, in lots of cases, these are just even extrapolations from a lot of these models for intensity are just extrapolations from low redshifts, and the ones at high redshifts, a lot of these models are analytic. We don't want to do that, and so now a lot of work though has been developed to come up with simulations in order to do a better hydrodynamic simulations in order to do a better job of predicting what the star formation rate would look like. What the luminosities of the different objects from the gas would look like in order to make a more complete model of what the intensity from different lines would be. And we want to know this because this is just like there's a lot of work in developing simulations and emulators for LSST, you're going to want to do simulations of intensity mapping in order to be able to get better, do a better job of really constraining models, okay, for intensity, for the astrophysics. However, simulations are hard and very expensive. So Well, everything is hard, but simulations are expensive. So the idea being that, for example, this is a simulated box for the illustrious simulation, and so for one simulation for one box 300 megaparsecs on the side, it takes about 2 years to run one simulation. So that's very unfortunate. So I mean, well, at least for the big cosmic volumes, they come up with a new one every 2 years. And so, in particular, this is so we want to do it, and so that's for a smaller volume. We want to be able to simulate volumes that comprise our whole our whole intensity light cone, and so that's going to be very difficult to do because those volumes are much larger that we want to simulate. And also, too, we want to just we want to be able to, in particular, this is going to be a problem, and so what we've a method that has been developed, not specifically for this purpose, it's been used for many purposes, but it will be very useful for intensity mapping, is called semi-analytic modeling. And so in semi-analytic modeling, the idea is that, particularly in our case, the idea is that you can take you can use simulations to sort of develop analytic schemes for how you would take, for example, a halo with a particular merger history and be able to determine what basically what galaxies exist within those halos, how the stellar evolution happened, and also too, and from there you would get spectra to where you can then say, okay, what would be the intensity in various lines and continuum B. And so this would be so once we have, with this kind of modeling, the goal is to be able to develop line intensity mapping mocks, which we can then use both for forecasts, for testing foreground removal and estimators for measurements, and as well as possibly even using for when we want to take the data and then fit models of star formation or things like that. You could use a line intensity mapping mock in order to do that, and so that's the goal. And with the so this is work that my student Chungshi is working on. So right now we're working on developing intensity mapping mocks for various scales. For right now, the first thing we did was we just recently started to complete a full intensity map for a very small area. So basically this is for the aspect survey or almost spectroscopic survey, which only comprises 4.6 arc-minute squared, so a very small area, but this is galaxy survey. But what we were able to do first is we were able to calibrate, the luminosity star formation relation from data from aspects, and we were able to, and our SAM was able to fit that. So this is work that she was able to do, and this is work that we're doing in collaboration with Rachel Somerville. So this is sort of related, not technically part of, but it's related to the small collaboration with Rachel Somerville and Greg Bryan. So the idea is that, so this is the first thing we were recently able to do. She was able to recently do, and then next, she's recently been able to develop a light cone. So this is still the I believe this is still the 4.6 arc-minute square light cone, but she has just recently. So this is like how she was actually able to recently make a 2 square degree light cone. Okay, and this is used by basically taking simulations from the small multi-dark Planck simulation, and then stacking them together so that you can develop a light cone. Okay, and this is a light cone that varies over redshift 0 to 8. Okay, and so then right now it's running. She's running right now. It's currently in the pipeline on CCA computers. She's running the semi-analytic model on all these halos. So the 2D square degree has about 70 million halos. So right now she's running the halos in order to be able to make the intensity mapping mocks. And so this is what the goal is. So once we have these line intensity mapping mocks, the idea is then we can make intensity map. Once we have these light cones, run in SAM, you're able to get the intensity map mocks at multiple frequencies for all the lines that we want. Particularly in this case, we're looking at CO, C2. We're also making mocks for galaxy surveys because we can also predict optical bands as well, and so we can make mock galaxy surveys that we would then model cross correlations. And so the idea is that once we have the intensity mapping mocks, then you can model power spectra and 1-point PDF mock measurements with that. And so then from there, then you can use the models. Then you can do fits to be able to then constrain SFRD and keep the luminosity functions. That's what, of course, what we'd be able to do with the 2 square degree model. You have to, and so we'd be able to try to do those fits. We also have plans in the works in order to use the peak batch method developed at CETA in order to then extend this out to a full, at least the 400 square degrees that EXCLAIM would then map. Okay. So this is what the goal is for this type of work. And finally,
before you get it, could I ask, this is jointly to you. HOD is often the way that one tries to mock the merger history. Instead of trying to do an entire tree, trees can be done, but you're using the tree.
Yeah, specifically for this, we're using the extended pressure merger trees.
Okay, can I comment?
Well, I was looking to both of you.
So HOD, traditionally people have a single line, CO 1 to 0, and they relate that to halo mass. The advantage of this method is that we predict the entire CO ladder and C+. We could do 21 centimeter as well. We can do the optical emission lines because we have a physical model. So we get all of the lines self-consistently.
Well, the biggest issue.
I don't know how to do that with HOD.
The biggest issue that we're finding, and you have the name Keating there, who's working closely with us on this because we're trying to use the fire sims for it, is that the star formation is the biggest variable. And it's causing things to go all over the place. And my issue on this subject is that you have to somehow try and regress that huge variation out in order to try and get cosmology from this. So I don't know, is this technique going to be able to nail it better than we're doing?
Well, I mean, the advantage of this is that
can you reproduce star formation histories?
We can change the star formation recipes and see what the implications are for a particular map.
Because what we were seeing is, depending explicitly on the redshift, you can get the gas blown out and then it comes back in again, and it's an extremely random variable on our entire program, which our program is similar to. It's one collective program, right?
Yeah.
And so it's probably the biggest issue I see for this subject.
Yeah.
Longer conversation.
Yeah. Okay. How much time do I have left? When is the end time? Okay, great. I just have a few more slides. Now I'm just going to talk about this last section. I'm going to talk about the SPHEREx mission. So SPHEREx is just like EXCLAIM. SPHEREx is also a NASA mission, a much bigger NASA mission. So it's a mid-X mission, so it's like a few $100 million, I believe. And the idea is that it's going to, well, actually it's one part of 3 surveys. It mainly consists of, it's a speed mission. So the first survey is going to be a full sky survey, basically of all, a cosmic variance limited survey all the way out to redshift 1.5, I believe. And so this is going to be able to, and so the goal is to be able to use this, its main science target for that is to be able to constrain inflation, specifically to get errors for FNL less than 1. And so with this, the top, you would see this as various inflation models on it, and the idea is that with Planck is the sort of the big blue error curve, whereas Euclid is this light blue one, and whereas with SPHEREx you'd be able to get those small curves in there. And so the idea is to be able to it's the idea hopefully is that you'd be able to do very tell the difference between various models of inflation. The second survey is going to be a 200 square degree survey at the basically at the zenith of Earth, and so we're going to use that in order to measure. Well, we're going to be able to use that to measure the epoch extragalactic background life from the epoch of reionization. And so the idea is that we learn more about stellar evolution in that epoch through SPHEREx. Also, too, and then finally, there's going to be a survey, a galaxy survey, and this is going to be able to try to constrain basically ancient ices. So this is like the ancient sources of water within our galaxy, and the idea is that you can use that in order to learn more about how how water traverses through the galaxy, and maybe possibly even learn more about how water how water from the galaxy source water on Earth. So this is how the instrument looks like. Again, I'm not a telescope person, but so basically you do have this baffle here, and the idea is that this is going to orbit on the terminus, basically the line between day and night. One orbit is about 90 minutes, and so the idea is that it's going to be able to block out the sun, and so it's not going to need to be cryogenically cooled. It's going to be passively cooled. And so these are the specs. So it's about so it's going to map between wavelengths of 0.75 to 5 microns with sort of low to mid spectral resolution. So it's a lower spectral resolution instrument than EXCLAIM surveys. And it's going to, with the aperture of 20 centimeters. Okay. And one thing I just wanted to note is there's going to be opportunities for intensity mapping, in particular for the 200 square degree survey. There's going to be some opportunity for intensity mapping. It's going to be able to detect H alpha and Lyman alpha emission, Lyman alpha for redshift less than 5, and Lyman alpha for redshift greater than 6 or so. And so the idea is that there's going to be many opportunities. So there's some core science that the people in the SPHEREx team are going to do, but what I'm interested in is possibly thinking about cross correlations with many of these intensity maps. So in particular, I'll be interested in if you could cross correlate these with galaxy surveys, and where you could learn about the galaxy, where you can learn about the emission within structures that correlate with both the galaxies and Lyman alpha or H alpha. In particular, for the H alpha survey, hopefully with the Lyman alpha line, you can cross correlate that with intensity mapping surveys from reionization. And so that, in particular, what you'd want to see is, one possibility is to see Lyman alpha. It's tracing the ionized regions in the epoch of reionization, cross correlated with 21 centimeter, which is going to trace the neutral hydrogen in the epoch of reionization. And so you'd be able to see the topology of the IGM as reionization evolves, and you'd be able to see how reionization evolved over time. And also this would help to, particularly with the H alpha survey, to be able to learn more about the ISM and IGM by being able to do these types of cross correlations with other surveys, both galaxy and intensity mapping. And so that's something I'm really excited about. So in conclusion, line intensity mapping is uniquely positioned to be able to discover more about both astrophysics and possibly cosmology. Particular, I'm interested in the idea of using multiple lines. I think a multi-line campaign is really necessary to accomplish the full power of intensity mapping. Note that it's not just using the cross correlations, but it's using the cross correlations as well as the autos in order to get the full information from the survey. Well, from the 2 point at least, and then there's more statistics you go from there. There's also the possibility of intensity mapping, which I know some people here are working on, and like Paco, and so that's also another avenue that I find very interesting. And then so we were able to do some work with what we had with the Planck survey to be able to try to constrain C2, and we were able to detect an excess, but more work is needed, particularly with actual high spectral resolution surveys. And so EXCLAIM was going to be one of several surveys that are going to be able to pursue this, and so it's going to be, and SPHEREx is going to also have a role to play in this as well, and I'm very excited to see what's going to happen in the next few years. Thank you.
Thank you very much for the interesting talk, Anthony. So now we'll take any other questions, and we'll just let junior people, if you have questions, ask those first, please. Anyone, you can be senior or Paco.
Take off.
Count as junior.
So for the simulation, I guess that the maps that you produce are limited to the size of your simulation, right?
They're limited to the size of the simulation, otherwise you have repeating
Have you thought
correlations.
in using machine learning for this, to find the
Well, that's the thing. So you should talk to Avery. So we're actually, that's something that we're actually getting involved with. So in particular, even for the, but definitely if we want to do anything larger, for one, we're not going to be able to use the radiant bias simulations because they're too small in order to use for the initial seed. So we're going to have to use probably something like peak patch. But also too, even with that though, to run the SAM on all of those halos, like when you're talking about millions and millions of halos, it's going to be prohibitive to do that. So machine learning, we're looking at, Avery's looking into this. Avery and of course Rachel Somerville are looking into this as a possibility to be able to be able to use basically the SAM and use the SAM to be able to then very quickly, using machine learning, to be able to sort of effectively run the SAM very quickly much quicker on broad populations of halos in order to be able to do that population much faster than you could do if you were just running the SAM on each halo. So, yes, Dave?
So when you're doing traditional surveys to measure large-scale structure, I get to weight each galaxy equally.
Mm-hmm.
When I'm doing intensity mapping, I weight each galaxy by its intensity.
Well, sorry, are you talking about the observation or the model?
Observations.
Well, the observation, you're not measuring, you're looking at the pixels.
Okay, well, each pixel is the sum of the number of galaxies weighted by that, right? Weighted
But
by
the fluctuations, but yeah,
weighted
sure.
by the intensity.
Yeah.
So you're potentially subject to a lot of shot noise because of a handful of bright star, a couple starburst galaxies in particular, I worry would dominate the fluctuations. So how much of the fluctuations are dominated by things on the bright end, most massive end?
So this is something I looked into a while ago for I had a paper on looking at alignment alpha intensity mapping, and this is a big problem with that. So you can, in particular, those bright galaxies can seriously dominate the signal, and so on orders of magnitude. And so what you can do though is if you have ancillary surveys in the same volume, at least this is what you can do. At least this is what you do at redshifts where you have the galaxies. You can try to reduce. Well, of course, the bright objects are going to tend to be at the low redshifts anyway because they're closer. And so you can use that, and you can cut those. You can try to cut those pixels out, and it turns out that you don't actually reduce your constraining power too much, even if you cut out like a few percent of pixels or something like that.
And I guess so. The related thing for modeling that, if I think about sort of standard kind of HOD, you're saying star formation goes as mass, but here you have this stochastic part where some fraction of the galaxies there's a lot of scatter.
There's a lot of scatter,
mass
that's right.
luminosity relation.
And
how
that's
do you capture?
Well, so that's what we need. So there have been attempts to do it analytically. So there's a model in 2016 by Tony Lee at Stanford, who actually put stochasticity in models. But in particular with SAMs, we're going to be able to do a lot better to be able to actually include that stochasticity from the beginning.
So we did some sims with variable, try to characterize it. It's not uncorrelated, the fluctuations. And that needs to have a lot of further looking at. But basically you do a log normal scatter, and then it makes a big difference in the nature of the mass, as you might appreciate. So that's going to be one of the key things, and that was my comment about somehow we have to regress this out. And some signatures are more integrated over star formation history than other ones. CO looks like it's very sensitive, for example.
Further questions?
So yeah, you mentioned the CO and C2, and as a tracer for H2, which one is better basically depends on your cosmic ray population. And so
well, for H2 you want CO because it lives in the same cold gas region, so you want CO for that.
Well, I think sometimes C2 can be a better tracer, right, depending on the cosmic ray flux. So I'm wondering if anyone thought about, given the ratios of those lines, if you're able to constrain anything about the cosmic rays.
So I've never heard of the idea of using C2. So I know C1 is also a tracer of H2, and so but I think C2, it mainly lives in ionized regions within the clouds. So I mean, on larger scales, of course, but for the I mean, maybe you should talk about it. Maybe you could talk about it later, but yeah.
So Laura,
the bright C2 arises in regular parts. So not the
So that's more, whereas more the diffuse fainter ones occur.
So yeah, you do get C2 in the photoionized mode, but then that's, C2 is subcritical to excitation.
I see, okay.
So Laura had put in cosmic rays, and it made a dramatic difference. And so we don't know what the right value is, and maybe we could think of this as a learning experience for cosmic rays at high redshift, which is one of the great unknowns.
It's not only cosmic rays, also the overall.
Say it again?
It's not only cosmic rays, it's also the effect of photodissociation on the CL. That's your
Oh, yeah,
star formation.
yeah. Yeah, it's just that what was remarkable is
That's
the
the-
role that cosmic rays were going to play in this process, which had not been included in any sims before for this. So.
Mordecai, do you have a comment on this?
Yeah, I just was going to follow up and note that the so-called X factor, the CO to H2 ratio, is only constant across the Milky Way-like galaxies. Once you go to lower metallicity galaxies, it can vary dramatically.
And even in the Milky Way, it's not really a
So now that we're opening all sorts of cans of worms with the X-factor, cosmic rays, et cetera, it's probably a good time to transition to wine and discuss these things further.
Sounds great.
So let's thank Anthony again.
Thank you.